Okay, so I guess let's get started. So in today's tutorial, we'll be continuing our discussion on register allocator. Last week we basically stopped here where we showed. Yeah. So by the way, it's recommended that you open the GitHub repository and go to Tutorial8 and open the source file for the minimal register allocator and refer to it as we talk. I think maybe it's a better approach to have a better understanding of the register allocator itself. So yeah, let's. So this is again. So this benchmark is pretty similar to what we saw during the lecture. In the last week, we stopped here where we said, so in the case of machine function, an RVM machine function, we have slot indices, which basically is a unique ID assigned to every machine instruction that we have in this machine function. As an example here, so in the entry basic block, the slot indices will be ranging from 0 up until to 128. In the basic block on the left-hand side, it will be ranging from 144 up until to 336, etc., and etc. So the slot indices are really useful for identifying the live intervals, which we'll be describing shortly. Okay. Okay. So as we also discussed last week, the live range in this case, as an example, so the live range for A is shown here. The live range for B is this one. The live range of C is this one. And the live range of A is this. And the live range for D is this. Recall that, so we have to merge the live ranges due to finals. Okay. All right. So in the register allocator, let me erase the slide intervals. Okay, so as you can see in our current implementation of the minimal register allocator, we start by getting various data flow, not data flow analysis, but analysis results, which include the following. So the first result that we get is called virtual register mapping. From the virtual register mapping, we further obtain two other results. So the first is called target register information. And the second one is called machine register information. So what is the difference between these two? Well, target register information basically describes the target machine. Okay, so it is an immutable object. So because it basically is a description of the target machine, so therefore it is immutable. So let me put it here. So immutable. Whereas for the machine register information, it stores the information of the allocated physical registers and virtual registers. Physical and virtual registers. An important job that our register allocator to do is to materialize the virtual registers. That is, so to map those virtual registers to physical registers. That is the job of our register allocator. Any question here? Good. So this is on virtual register mapping where we have, let me just put abbreviation here, which we have, as we said, we have TRI, which stands for target register information, and MRI, which stands for machine register information. Okay, and the second analysis that we'll be getting is called live intervals. As we can guess from its name, live intervals basically indicates the live ranges of our variables, or the live range of each virtual register. Live range for each. So as an example here, so if we go back to this micro benchmark that we had, and we query the live intervals for the variable A, which as we shown is basically up here to here and here to here. What we'll be getting is, let me write it here. So the live range of A, as we run the register allocator, is shown as those two intervals. Okay, where the first one, 64 to 240, indicates the live range starting from this point, which is 64, so up until the point here, which is 240. And the other interval is given by 352 and 448. Okay, so this interval indicates the region starting from here, which is the starting slot index for this basic block, up until the use of A here, which is indicated by 448. Okay, and furthermore, live intervals provide you with more information other than simply the live ranges. If you check the outputs of the live intervals, you will notice that so after each live range, you have a small index 0. So this index 0 tells you so at which point is this A first defined. Okay. So as it will further output that this 0 indicates at which program points this A is defined, which is 64. And furthermore, the live intervals also has another weight associated with it. However, this weight is initialized to be empty. Not empty, but initialized to be 0. 0 initialized. So that is 3 pieces of information. Live ranges, the definition for each live range, and also the associated weight of each live range. So this is basically what the live intervals analysis tells us. Any question here? Yeah, if you don't understand anything, just type in the chat and I will re-explain it. Okay. So this is the first thing, virtual register mapping. Second thing, live interval, and third thing is live register matrix. Again, so we can infer from its name that so it is a matrix, right? So basically, it's a 2-dimensional array. Whereas the first dimension, so one of the dimensions is given by slot indices. So I will simply use the abbreviation here, slot indices, SI. And the other dimension is given by the register units. So the live range matrix is used by currying interference between relationships between the different registers, because it is a 2-dimensional array where we have slot indices and register units. As you can probably imagine, so later, I think maybe it's better to switch these two, where we have reg units here and SI here. Where, as you can imagine, so suppose that we have a register that sits in the register file for a certain region. So this will be indicated as an example as a line here. And we have, for instance, another register, for instance, that sits in the register file for this line. Starting from, so this is basically a starting slot index, and this is its ending slot index here. So as a more concrete example, so suppose that later on we materialize the virtual register A. So what happens is that so the physical register allocated for A will sit in the register file starting from slot index 64 up until to 240 and 352 up until to 448. This is basically what the live register matrix does. And it is used for when later on we want to query the interference results. Any question? Yes, that's right. Okay, so now that we are familiar with all the analysis results, let's have a look at how the minimal register allocator is implemented. Oops, I erased the slot, but anyway. Okay, so in the minimal register allocator in the minimal register allocator implementation, as you can see from its main method run on machine function. So the first thing that we do is that so we enqueue all the virtual registers from the machine register information to a queue, to a FIFO queue. Okay. So first thing, enqueue all virtual registers. From MRI. As you can see from the implementation, the data structure that we used for the queue is a FIFO queue, right? So that is so. FIFO queue. Do you think, and later on, like when we try to materialize the virtual registers, we'll be popping from this virtual FIFO queue, like of course in the first in, first out order. Do you think there's a better implementation of this? Of course, this implementation is greatly simplified, but do you think there's a better implementation of this FIFO queue? Assuming that given what we have described previously. So first of all, is this clear? So the first thing that we do is that so we enqueue all the virtual registers from MRI. The reason is because the main goal of our register allocator is to materialize all the virtual registers from MRI. So that is the main goal of our register allocator. And the question, so the way we enqueue this in our minimal register allocator is using a first in, first out queue. That is so in the order that they appear in the machine register information. But is there any better implementation than this FIFO queue? So the hint is that, so recall that previously we discussed that for each live intervals, there is an associated weight with it. Assuming that so this weight is properly initialized, assuming that so let's just suppose that we initialize it using the method that we have described during the lecture, that is something similar to number of definition plus uses multiplied by 10 to the power of loop depths, divided by the degree. Assuming that so this weight is properly initialized, what do you think can be a better implementation than this FIFO cube? What do you think? So first of all, is this point clear? Is this in Q all virtual registers from MRI clear? And second thing, do you think there is a better implementation than a FIFO, than a simple FIFO queue? First in, first out queue. What do you think? Based on yes, exactly. So let's an improvement of this implementation is so we leverage the weights as is described here, and we want to prioritize the live intervals that have higher weights, right? For instance, if let's say a live intervals is used in a loop body, then we want to prioritize materializing that virtual register. Any questions? So, and after enqueuing all the virtual registers from MRI, we'll be then popping, we'll be then dequeuing from this queue. Namely, so while the queue is non-empty, we'll try to either allocate or splitting the virtual registers. So how are we going to do that? So by splitting, we mean spooling. So how are we going to do that? So the way that we are going to do this is that first we obtain a plausible allocation order. 2.1. Plausible allocation order from TRI. Plausible order from TRI. As we described before, so TRI, which stands for Target Registered Information, is an immutable object or immutable descriptor of our target machine, right? So the first thing that we want to do is so we want to ask the target machine that I want to allocate a physical register for this live interval, which is of certain register class. So a register class is basically, think of it as the type for the live interval. For a certain register class, could you please give me a preferred allocation order for this register class? So this is the first thing that we do is obtain a plausible allocation order from the TRI for our live intervals. Any question here on this step? Oh, so a register class, so it's basically the type name for our live interval. So as an example here, in the micro benchmark here, we initialize the A to be an int. So as you get its register class will be tells you, so it's called GR32, but it's actually denotes, so think of it as 32-bit int. It's just basically the type name for a live interval. So yeah, so you will be telling the TRI, so what is the register class of your live interval, and it returns you a plausible allocation order or a preferred allocation order. Okay, so this is the first thing that we do is, so first obtain a plausible allocation order. And the second thing that we'll be doing is query the interference. Query. That is, so after we have obtained this allocation of preferred allocation order from PRI, that is, so PRI will give us a list of registers, as an example, physical registers, R1 up until blah, 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 to let's say R32. So this is in the preferred order, that is, so we prefer to allocate in R1. So R32 is the least preferred, okay? The second step that we'll be doing is to query interference. That is, so we'll be traversing through this preferred order. And for each physical register, we'll be asking, so again, so this is a pretty simple heuristic. And for each physical register that we'll be asking, can we allocate, let's say, live interval A, can we materialize live interval A using register R1 and so on and so forth up until to R32. Is this step clear? Okay. And as we query the interference, we'll be getting 4 different results. So as we query the interference, as you can see from the implementation, we're getting 4 different interference results. So the first one is called free. As its name indicates, this just means that so the physical register is free as this for this live interval. So we can just simply go ahead and allocate it. So this is free. The second interference kind is called virtual register. What this means is that so the physical register, that physical register has already been allocated by another virtual register. As an example, in this case, let us suppose that so we allocate, let's say B, virtual register B before virtual register A. And let's suppose that we allocate B to sit in physical register R1. In that case, as we query the interference for A on the physical register R1, it will return us this virtual register. That means that this R1 has been already occupied by another virtual register B. As you can see, this kind of virtual register this kind of interference can be resolved by removing the other virtual register. So what this means is that suppose that, again, the same example as what we have described before. Suppose that we allocate register 1 to B. And suppose that we really want to allocate register 1 to A. We can assign virtual register B to something else, as an example, so R2 amounting to R32, and assign physical register R1 to A. That is, again, so virtual register interference can be resolved by removing other interference, or removing the interfering virtual register. Is this point clear? And the third, so this is the second type, which is virtual register. And we have two other types, that is so register units. And furthermore, register mask interference type. So what register unit means is that, what register interference, what register units interference means is that, so suppose that we have a function call, let's say print. Let's suppose that we have a function call in our program that says print percentage D and I. What happens is that, so in this case, we'll need some physical register to store this string. Let's say we need a physical register to store the value of this string. And as we try to materialize the virtual register for I, we cannot allocate it to physical register R1. The reason is because so R1 is already used to parse in the function argument for print here. So this is called register unit interference. That is, so this physical register has already been used to pass in the function argument for a function call. Or think of it as if like this physical register has already been preoccupied, not by another virtual register, by some, like let's say some other function arguments call. And this, the register unit interference, as you can see from this example, it cannot be resolved by removing the other interfering virtual registers, because there's no other interfering virtual registers in this example here. And finally, the interference result we might get is called register mask interference. So what register mask interference does is that Suppose that we make a function call in our program. Let's suppose that it's here, which is also what how our benchmark is implemented. We here instead use A to assign another variable, we instead invoke a subroutine called use A. That is a function call. So as we invoke this function call, as you can imagine, certain registers will be modified by this function call. And there is an agreement between the caller and the callee that what registers that the callee should preserve. So this is called callee preserved registers. Callee, and another name for callee preserved registers is called call preserved. Call preserved. The nice property of the callee preserved register is that as its name indicates, its value is preserved by this function call. As an example here, suppose that we are hoping to materialize the virtual register C. We are hoping that the value for C is untouched by this function called use A. Right? So therefore, we are hoping to assign C to certain callee preserved or call preserved registers. So those are the same thing again. To certain call preserved registers. So how do we know the call preserved registers? Well, as we invoke the function call here, as you can also do experiments at home. As you will probably notice that after this call certain function, you will have a register mask operand. The register mask operands tells you what registers will be preserved across this function call. It tells you what will be preserved by this function call. So on the contrary, since we have callee preserved, we also have caller preserved. And this is equals to call clover. So the name caller preserved is pretty confusing because it is not preserved at all. Right? This just tells you that, if let's say you want to allocate, let us suppose that R1 is a caller preserved register. Then it is the responsibility of the caller, that is our program here, to stash the register R1 to the stack and unload it after we have made the function call to use A. So as you can see, going back to the interference kinds that we had previously. So by register mask interference, we mean that this virtual register is live across a function call, right? And we do not hope that the value for this register to be modified, and therefore we are hoping to assign it to certain call preserved or callee preserved registers. Is this clear? For a register unit interference and register mask interference. Yes, that's right. Because it is the responsibility of the call E to preserve those registers. And therefore, it is always safe to assign. Let's suppose that R1 is color preserved and R2 is call E preserved. It is always safe for us to assign C to R2 because it is the responsibility of the function subroutine used to preserve R2. However, for R1, if we can still assign C to R1, however, it is not preferred because we have to do extra operations to preserve the value for R1 onto the stack. As an example, by stashing onto the stack and reloading it from the stack after we make the function call to use A. Okay. So now that we have described the interference kind, and the third step that we'll be doing, which includes those four: free, which is go ahead and allocate it; virtual register, meaning that it's already being occupied by other virtual registers and can be resolved by removing the interference other registers. The register units, meaning that it has already a fixed physical registers is used to pass in function arguments to function call, and register mask, which is related to call E preserved registers. Okay, so this is basically our second step of allocating and splitting the virtual registers. And third step, so in the case when we cannot materialize the virtual registers, what we'll be doing is so we spill it, or in other words, split the live ranges. Spill virtual register. Or in other words, split it. So as an example here, so suppose that let's say for virtual register A, we do not find anything, any physical registers available to allocate virtual register A. What we'll be doing is so we'll be splitting its live ranges so that we'll be stashing the value of A onto the stack here. Of course, this is not a very good example because A is used here. Let's suppose A is stashed onto the stack. So here we mean that so it's stashed onto the stack here. And then we reload it at each of its uses here. We reload its value from the stack every time. So this is what we mean by spilling the virtual register to the stack, and that is equivalent of splitting its live ranges. So yeah, as you can see, we use the built-in spiller from LLVM, which is called the inline spiller, for doing this spilling. And yeah, you do not have to worry about this for your assignment. So first, sorry, any question here? Oh, yeah. So which registers are call preserved or call E preserved are determined, of course, determined by the target machines. As an example, so in the x86 machines that we'll be dealing, so you'll be notice something like EBX is call preserved, whereas EAX, ECX, EACDX are color preserved or color clover registers. Yes, they are determined by they are the properties of the target machines. Yes, and of course they are obtained by, again, the target register information. Any questions on the spiller? Yeah, I think. Okay. So I have a question here. So suppose that, so after splitting, let's say splitting the life interval of A into those sub-intervals, okay? What do you think shall be the weights associated with those life intervals? So the inline spiller will automatically assign weights to those associated to those splitted life intervals. So what do you think shall be the associated weights? Let me give you several options here. The first thing is 0. Second answer says infinity. And the third answer is some random value, x. What do you think shall be the weights associated with the splitted life intervals? Well, maybe try this at home and see what is the answer to this question. Like suppose that suppose that you split certain life intervals, which can be obtained, which can be done by simply skipping the previous allocating the physical register steps. Try to see like what is the weight associated with the split life intervals that you got. Okay. And yeah, this basically concludes. Okay. So yeah, this basically concludes the implementation of our minimal register allocator. Any questions here? Good. So now that we have time, let me check. So now that we have time, we can briefly cover again. So think about this question at home, right? So what is the associated weight for splitted life intervals? So in terms of the programming portion, so one of the biggest challenges in the programming portion is to deal with the fine nodes in the case of liveness and also the lazy code motion analysis. So how should we deal with the fine nodes? Well, let us consider this simple example where we have A1 in one branch, A2 in another branch, and we have those two merged to the same variable A, which is phi A1 and A2. And we use A. So in the case of liveness, which is a backward analysis, if let's say we simply treat, let's say, variable A, we treat finals as normal instructions. That is, so we set both A1 and A2 as live, starting from this program point here onwards. What we'll be seeing is that so we'll have A2 live starting from this program points onwards. Similarly, A1 live starting from this program points onwards, which is obviously an incorrect solution. So what should we do here? As we can see, we are hoping to set A1, instead of setting A1, both A1 and A2 live, starting from this program point onwards, we are hoping to set A1 live on this program path here, and A2 live from this program path here. Right. So therefore, we are hoping to get, so as we notice, so variable A is live here. We are hoping to set, as we getting, so this is just my implementation. Of course, there are other equivalent implementations for this method. As we get the boundary values for this basic block, we are hoping to set A1 active here. If we notice, so variable A is live at this program point here. And similarly for A2. That is, so we unpack finals to incoming values. Unpacked phi as incoming values. Any question here? Okay, so since this is already 4 past 11, I guess, so let us stop here. And in the next tutorial, we'll be discussing about the theoretical questions and some hints for assignment 3. Okay, so yeah, thank you so much for coming. And yeah, if you do not have any questions, you are free to go. Thanks.